This is an introductory video for discrete mathematics. We're going to look at this problem and understand it. Not because we're going to be tested on it in the future, but because it's different from what you might have seen before in any other math class. And its solution also might be different from anything you've seen before. Pause the video and quickly read problem 1. Now this is an open-ended question. I didn't say whether such a root existed. If a root does exist, then we can just draw it. Right, and be done with it. But if we think a root doesn't exist, we can't just say, I can't find one. We must prove such a root does not exist. Okay? We have to prove it using logic. I guess in theory we could use brute force, but that's going to take, like, trying all the possible roots. That's going to take too long. I don't want to do that. Okay? Now, method 1 is clearly easier, but that doesn't mean it's correct. But let's try it, right? Pause the video and try your hand with it. See if you can come up with a root, a continuous root that passes over each bridge exactly once. You can visit each landmass multiple times, but you can cross each bridge only once. Right here are my attempts. No, that didn't work. That didn't work. I'll go here. That didn't work. That didn't work. And here we go. That didn't work. Boy, that doubly didn't work. Maybe here. Oh, this looks promising. Maybe not. Thought I might have had that last time. So at this point, you might say, well, maybe there isn't really a root. And in fact, you would be correct. Leonard Euler, possibly the greatest mathematician ever to live, showed in 1736, almost 300 years ago, that no solution can exist for this problem. And he did, in fact, show it. He wrote up a proof of it. And he did it by inventing a subject of mathematics called graph theory. This solution to this problem is considered to be the beginning of graph theory, the invention of graph theory. So we're going to see what he did. What he did was, if you just keep this landmass in mind, right? He took this setup in mind. He took each landmass and represented it with a dot, right? So we see 4 landmasses, A, B, C, and D. Oh, no, sorry, this is C, B, and D, right? And for each bridge between landmasses, he represented them with a line, or what we call an edge. I know I'm drawing curves, but just pretend that they're lines, right? It doesn't matter the shape of the line or the length of the line or anything like that, okay? So even though this graph here looks a little different from the landmass, the structural integrity is the same. The connections between the landmasses are the same. And we're going to now prove something about this graph, and in turn prove something about the landmass on the map. So what I've done is I've written out the proof, but I've also scrambled the steps. So it's going to be our job to unscramble the steps. Now I'll start us off. You can pause the video first of all and read this little paragraph right there, those 2 paragraphs. We're going to prove these things in claim-proof form, which means we say the word claim, and then we make the claim. And then we're going to say the word proof, and we're going to write the proof. Okay, so those are the first 3 steps. Now I'll go 2 more steps, and then I'm going to let you try to do the rest. The whole point of the proof is to model it with a graph, and so that's what we did. That's step number 11. Then we make an observation about this graph. Right, we call it G, always good to label our stuff, and we know that it consists of 4 vertices and 7 edges, right? 4 dots, 7 lines. I'll give you one more step, which is that the last step of the problem is going to be that box. Okay, you end a proof of the box. Okay, just to let the reader know you're done. Pause the video for 5 minutes, see if you can fill in the rest of this proof. All right, next up, it's going to be step 6, because now that we've transformed the graph, or the map into a graph, we're going to prove something about the graph, right? All right, now at this point, we make an observation about our graph, and then we make an observation about the trail. And then we justify that observation. And then we say, well, hold on a second, we've got a problem. Oh wait, try J and then K, right? And I think that's the end of the proof, right? Step L, right? Last step. Now, I intentionally did not go over these steps very much. I want you to sit with this, look at it for another 5 to 10 minutes, see if it makes any sense. If so, then wonderful. You did better than I did when I first saw this proof. If not, then come to me with questions for the next class. Let me know what you think. Okay, let me know where you run into some problems, okay? But anyway, we're going to move ahead, okay? And we're going to say the following. There's nothing special about the map of Konigsberg. We can generalize this to any graph, right? So we'll say, if a graph G contains an what we call eulerian trail, i.e., a trail containing all edges of G, then G has at most 2 vertices of odd degree, and these 2 vertices are the endpoints of the trail. Okay. Now I want you to pause the video and do this. It might take another 5 to 10 minutes to do that. Well, I'm going to go ahead and do them, and here's what I got. I think this one is Eulerian, right? I think we can get away with this. Oh, maybe I didn't do it right. I think I didn't do it right. Well, just as well. Let's try that one again, right? So where are vertices of odd degree? Actually, this is a vertex of odd degree, and this is a vertex of odd degree. So actually, those are going to be our starting and ending points, right? So let's see if I go like this, and maybe I go around, and I do this. Yeah, I think we're good. So that's a check mark. Yay. This guy, I think this guy should also work. I think every vertex has even degree. So I'm not sure it really matters what we do. Yeah, that works just fine. I think we could just quickly see that this is not going to work out. Right? Okay, so let's try this guy. I think adding that extra edge made things work out okay, because if we start here, and we go here, and here, and then here, and then look, we're fine. Yay. And then if we keep doing this, I think this one should work too. We have any vertices of odd degree? We do. But if we just stop, and if we just start at one and at the other, I think we're good to go. And then this one, I used to draw these stars all the time when I was a kid. Did you? Yeah, so that one was not so bad. So I just want to point out, we are suggesting something maybe a little stronger than Proposition 2, right? Because Proposition said 2 said if we're able to get an Eulerian trail, then it's got to have at most 2 vertices of odd degree. We went ahead and said, no, every time we had at most 2 vertices of odd degree, we were able to find an Eulerian trail, a spanning trail. That's a little bit different, right? This suggests the converse of our state of proposition 2, right? If a graph G has at most 2 vertices of odd degree, then G contains an Eulerian trail. But again, that means that it contains a trail with all the edges, that hits all the edges exactly once, right? So if we combine proposition 2, which we already proved effectively, right? We could do the same thing that we did earlier with proposition 2, and conjecture 3, which is something we believe to be true but haven't proved, then we get conjecture 4, which is to say a graph G contains an Eulerian trail, I'll call it T, if and only if G has at most 2 vertices of odd degree, and these 2 vertices are the endpoints of T. Okay? We'll take a look at this in a few months. In the meantime, you can go ahead and take a look at the writing assignment number 1, which you can find in Files under Writing Assignments. That's all for today.